right, the next phenomenon we're going to talk about, kind of a standalone issue. Creep is elongation, so it's a change in length. Any change in length can be evaluated in terms of strain. So creep is the strain or elongation of a material over a greatly extended period of time. The rate of creep increases as a material is heated, and we've got an equation for it. The change in strain over a change in time is A sigma to the n e to the negative q over RT. Any e to the negative something or other phenomenon looks like that. So e to the positive something is exponential decay, and or logarithmic decay, and e to the negative something is sort of an increase up to some limit value. So as something is heated up more and more, we might experience more creep. Q is the activation energy for creep. Essentially what we're going to find at the end of the day on this is that we've got an equation here. They'll give you all the values to plug into it, and you will need to do so. R is the only value you might count on finding somewhere in the handbook for a given material. R is the ideal gas constant. And we'll talk more about that in thermo, but it's the same fellow. T is temperature. Make sure you put temperature in absolute units as instructed here. So R and T go on the bottom. Q is the activation energy. Expect that value to be given. Though I think there might be a default value on page 99 in this section. I don't recall. That's the exponential function. Make sure you know how to find that on your calculator. Don't forget the negative sign. Sigma is the amount of stress we've put on something. And N is an exponent we'll put on that called the stress sensitivity. And A is probably the most important factor here. Remember that A is not cross-sectional area. It would be nice if they acknowledged that there were in fact 26 letters in the alphabet, both uppercase available as well as lowercase, plus every Greek letter known to man, but instead they use A, which we usually use for cross-sectional area. You're going to see NCS does that a lot. They take V and A and things that we use for one thing, and they just sort of repurpose them. So A is an area that's a pre-exponential constant. Expect that to be given to you as well. Basically, this becomes a math problem you plug in. Where is creep an issue? Well, where do we use something for extended periods of time where their dimensions get to be very, very important? One of the main areas in which creep is important, well, one of the areas we see creep happening often, well, a sort of classic example, is panes of glass in medieval buildings. So antique glass tends to have a slightly rough appearance to it. And panes of glass in, medieval churches and that sort of thing will be thicker at the bottom of the pane of glass than they are at the top. Why? Because they've stood vertically in place under a slight amount of stress, just the force due to gravity, for hundreds and hundreds of years. And so that's creep. In this case, the creep is not so much motivated by temperature, but by time. All right, in the shorter time frame, it's going to probably take a more sensitive material or a larger temperature for this to happen. And where do we see this happen? Well, what is a high temperature situation in which dimensions are extremely important?